Hello everyone, my name is Oveyes Sheibani and I would like to make these videos about a discussion about the quantum theory of the fields or quantum field theory or QFT. This is a very interesting subject. It is something that usually comes out after the quantum mechanic when the physics student learn general quantum mechanics, then they move to quantum field theory because that's the framework to basically calculate the cross-section of elementary particles. And it is a very actually useful framework even for further calculation. Right now, there are some books about the relationship between the quantum field theory and even financial markets. And in a very large scale, even we think of the population and the behavior of the human also can be explained and modeled by some form of random behavior or quantum behavior similar to quantum behavior of elementary particle. But the fundamental argument is something very accurate. It's about a space-time, a theory that connects a space-time and define an entity that you call it a field. And we should really explain what is a field is. The idea that we initially have from the field is coming from classical physics. But then we think about a process that is called the quantization of any variable. So when we quantize some physical entity, some physical observation and physical observable, we can think of them as the theory that it is quantized. And we are going to explain how it could be related to the theory of the field. So before I start to go into quantum field theory, I want to start with the question of what theory is valid in certain region on energies. For example, I start with a classical theory and ask the question that what kind of world, what kind of universe is well explained by classical mechanics? Basically, the classical physics or classical mechanics, classical electrodynamics are theories of differential equations of the field. And the idea is to find the evolution of the field in time and space, and somehow the value of those fields are what we are thinking them as the physical observable. So there is a connection between the value of the field and what we are measuring. For example, I say classical field is one framework of description, and then classical particle description is also something, and when they are mixed together they can explain wide range of phenomena. So electromagnetism, for example, hydrodynamic, and even by the classical particle we can go to statistical mechanics, and explain the behavior of gases and systems. These systems could be solids, or systems could be liquid. Even in solid state physics, you can use a lot of classical particle assumption, and it gives you a very good description of the system and the behavior of the system. So we have this classical physics, and the idea is that the dynamical variable that we want to find out is proportional to the value of that field. So the value of the field is something that we calculate, but the quantum extension of it is something adding more into this description, and we are going to say how could it be. But first of all, we can ask this question of what kind of physics is classical physics and what kind of physics is quantum physics. So we have this de Broglie wavelength, probably you saw it in the elementary discussion about quantum mechanic development in the early 20th century, that a French physicist named Louis de Broglie, he proposed an idea. He said that even massive particles such as electrons or matter, they can have a wavelength, and this wavelength is somehow proportional to the inverse of the momentum. So that was revolutionary. This is basically uncertainty, the inverse relationship between length and momentum in the wave description of the particle, and then some h bar constant here. And this du Broglie wavelength was predicting that if we have a lot of momentum, then the wavelength is going to be very small. And for a massive particle, or very large particle, ordinary particle that we deal with, like a soccer ball, I don't know, a car, a human, anything in a classical world, even smaller than that, even we can think of it as in the very small scale, similar to the life scale, even the cells, the life, and those sorts of things are also can be explained by classical physics. But when we say massive particles, we're basically talking about particles or systems that are like probably 1,000 times more massive than elementary particle. 1,000 times, even more than that. So let's say when we're talking about a soccer ball, human scale, and things around us, this mass scale is so much more than elementary particle scale, many order of magnitude. And we know the definition of the momentum is mass times the speed, and even relativistically we can have this gamma factor. But this gamma factor in the ordinary scale goes to 1. So because none of us are really going near the speed of light, every speed on the earth, relative speed of objects are not really comparable to the speed of light. So in the non-relativistic description of the system, P is equal to mv, and even if we think v, the speed of the objects are not that much, the mass of the object compared to the mass of elementary particle is a lot. So if mass goes to infinity, P goes to infinity, and then lambda goes to 0. And it looks like that lambda, or like quantum characteristic wavelength, let's say it's a wavelength that characterizes the quantum behavior. And by quantum behavior, I mean the wavy nature of particle, even the particle nature of the waves. So somehow interference pattern of those things, quantum interference pattern that shows some non-trivial effect that we expect from classical physics. So when the characteristic wavelength is so much smaller than the size of the system, and this size of the system is not something very accurately defined. So size of the system, let's say, can be proportional to the volume, and it can be proportional to the L cube. And this L is basically the characteristic length of the system. So lambda, when lambda is very, very smaller than L, I basically have a very large system. Let's say this is my system. Oops. So this is my system, and this is probably the characteristic length here, and then this is the objects. This is the wavelength corresponding to the objects. So this wavelength here, this lambda, is very, very smaller than this L, and somehow similar conclusion for hydrodynamic. This is similar to what we do in hydrodynamic. In hydrodynamic, you calculate some characteristic number, and then you compare it to the size of the system, and then you decide if hydrodynamic is a valid description of the system or not. But if lambda is very, very small compared to L, then that means the quantum effects are really negligible in the larger scale structure. So we can use the mean field approach, or we can think of the field to describe the system as the very average behavior of all the elementary particle and even non-elementary particles. So it's a construct it's an upward construct. That means that your fields are effective field. But something very interesting is that in electromagnetism, this A mu of x that gives us E of x and t, yes, there is an x and t, but anytime I write x, probably x means a space-time. So when I say x means space and time. So usually talking about the 4-dimensional vector here, and the first component is time, and the second component is x, and then there is a Lorentzian signature that t squared minus x squared gives us the space-time length, or space-time length in relativity. But anyway, so E, or electric field, is something that we think of it as macroscopic. So that's like the field created by a stream of particles. And somehow it's very interesting that we can quantize this field, exactly same mathematics, to gives us the behavior of even one single photon. So there is a very interesting connection between the classical limits and quantum limits. Somehow in classical limits, we are able to see structures that we can apply to quantum physics. So when the characteristic de Broglie wavelength of particle is so much smaller than the size of the system, that means the system is very well described by a mean field approach or effective theory. And somehow our system is classical. Now let's go to quantum system and ask the question of what is then a quantum system. A quantum system is where lambda is it's at the same order of magnitude with the size of the system, or even could be larger than the size of the system. So when lambda is comparable to the size of the system, then we have quantum effects. Then we can talk about energy scale. Then we can talk about time scale, mass scale, and again momentum and lambda. But all of them can be encoded into time, mass, and energy somehow. And these are like more fundamental units. So now we have two descriptions. I call the first one quantum particle, or let's say quantum particle, or even classical quantum mechanics. This word classical can be abused a lot because anything that it is not really quantum mechanical in a real sense is classical. Classical quantum mechanics. And that's basically the procedure that you quantize the dynamical variable of x as a function of t and momentum as a function of t, and you create a wave function. So that's basically is standing on this idea that the behavior of one quantum particle can be explained by a Hamiltonian or Lagrangian, consists of one kinetic part plus some potential part. And this potential part is not really something fundamental. So this is the kinetic and this is the potential. So something like a hydrogen atom. So hydrogen atom was a big success for quantum mechanics because it could explain all the spectrum of hydrogen with just knowing some constants of the nature. That was like amazing. So the idea behind it is that the electron is here and the proton is here. And then there is a stream of photons. It's a lot of photons exchanged in time. But this stream of photons are like the characteristic energy that they are carrying as a probe or as a projectile, let's say, is so much smaller than the mass of the electron. So I say the energy of the photons here are so much smaller than the mass of electron. So that what does it mean exactly? Exactly, it means that the photons that are exchanged are not able to destroy the electrons or create new electrons, because the characteristic energy that they are carrying is not really enough to destroy or create new particles. And those kind of systems are mostly, we call them elastic system, let's say elastic scattering. Eventually you see in particle physics and elementary particle physics, and in a lot of them, the world is seen as the window of a scattering. That means that I have something here, let's say it's a thing, I just call it a thing, and then I send something as input and I take something as output. So really this is called a scattering. Something goes in, something goes out, and our job is to predict what's going in and what's the outcome with some probability or even some determinity. But however, I say I have two kinds of scattering. I have elastic one, let's say elastic nature, And then we have some inelastic nature. So the hydrogen atom is the first kind. It's an elastic nature. That means that the photons they're carried by the photon, it's like a kind of coarse-grained photon again. So in one level, we don't have to go to the fundamental field of the particle. We can just explain this kind of physics with a kind of particle description that it is quantized. So now we talk about elastic kind of quantum mechanics, particle quantum mechanics. Now we have inelastic quantum mechanics or inelastic nature, when the energy of the projectile is comparable to the mass of the particles. For example, in the case that even I have an electron here and I have a positron here, so maybe I'm cheating a little bit here because I shouldn't tell the positron exists. There is a logical procedure that you realize for any kind of electron, there should be a positron. But let me skip and use the advantage of being at this time of humanity and say if we have electron and positron, and both of them are like really going toward each other with relativistic speed. That means the energy that they are carrying, is really comparable to the mass of electron and positron. Now let me talk about numbers a little bit. What do I mean by energy is comparable? So, in elementary particle physics, again, using the units that we use every day, like SI unit for energy in time, seems to be a little bit ridiculous, because those units of energy that we are using is good for the world around us. For the elementary particles, it's so large. For expressing the energy of the particles, elementary particles, and electron, it is more common to use the word electron volt. So, the mass of the elementary particle is also expressed in terms of electron volt. So the mass of the particle are a varied range of kilo electron volt, mega electron volts, and there is not particle that we've seen around 1 tera electron volt, but there is a possibility that even those kind of masses exist. However, when we say the energy of the relativistic heavy ion collision is comparable or even so much larger than the mass of the electron, sometimes there is this possibility in heavy ion collision that this energy is comparable to the mass of electron. So this number E can be starting from a few kilo electron volt. This E could be around some mega electron volt, and this E could be around giga electron volt. So this is the scale that we usually talk about, the energy of the projectiles. So this kilo electron volt is not comparable to the mass of the electron. So the mass of the electron is a few MeV. The mass of the electron is around 0.5 MeV. So if you are using photons around kilo electron volt, you're basically dealing with the regime of X-ray photons, and these are like in a probably elastic region for the electron. But if the energy is MeV, then because the mass of the electron is 0.5 MeV, then we are triggering the inelastic nature of the scattering. And if the energy goes to GeV, which means that the current energy that the heavy ion colliders or even electron-positron colliders are working operational, it's around a few hundred GeV. So it's very good to probably probe the quark and very higher mass particle. But I just wanted to say the activation of inelastic nature is around MeV and the GeV. So when I'm talking about the energy of the photon, around that relativistic energy like that, this photon is exchanged, and the energy of this photon is proportional somehow to the energy of the system. So when two elementary particles are near each other somehow, and each of them has some energy, let's say, the probability that exchange some very energetic photon is proportional to the total energy stored in the system. So in general, when the energy of the system goes up and become comparable to the mass of particle, then we can have a scattering with different outputs. Some of them have 2 outputs, 3 outputs, even hundreds and thousands of particles as an output. So this dependency on the number of particles is something very right now a very hot topic in the field of heavy ion collision. People want to understand what's the relationship of the multiplicity of the system. That means the number of particles that comes out of the collision with the energy of the system. And it is a little challenging to find dynamical relationship between the energy of the system and multiplicity. However, when we are in this energy scale, so we need a kind of field description of the particle, because simple quantum mechanics cannot talk about creation and annihilation of the particle. And there is one extra and last probably reason that we have a motivation to go to quantum field theory instead of single particle quantum mechanics is taking account the relativistic effects. So relativity is some principles that were discovered at the beginning of the 20th century by Albert Einstein, and it was mostly about the causal relation of space and time, and putting a limit on the speed of propagation of a signal. And relativity, there are some principles such as Lorentz invariant. So we have this Lorentz transformation, and Lorentz transformation are relativistic transformation, and they kind of keep the length, the space-time length of the particle invariant. So we talk about space and time with Lorentzian signature, and then the field equations that we are writing down should somehow be relativistically correct. So the problem with quantum mechanics was that, imagine if we have a free particle, and this free particle is a particle that is not really bound to anything. We have these two kind of Hamiltonian that we can write. We have the classical Hamiltonian, which is p squared over 2m, and we have the relativistic Hamiltonian relationship, or relativistic relationship between energy and momentum, and that's Hamiltonian squared is equal to m squared plus p squared. And then we are dropping a speed of light, everything equal to 0, it goes to convenient unit. And then, for example, I can say h is somehow plus minus the square root of m squared plus p squared. So we can see there is a different behavior of h and p in classical limit and relativistic limit. Now the question is that if I have a quantum mechanical particle and I want to calculate the propagation amplitude of a free particle, I have to calculate something like this. So I have my x0, let's say it's initial position, and then I have the evolution of the system in the Hamiltonian times t, and there is also an h bar, but that we talk about it again. We have to drop all those units, get rid of those constants. They become a little bit confusing, but we don't care because we have the ability to put any constant to any origin. And then there is some final state here, and we want to calculate if this number goes to 0 when the final destination of the particle is so much larger than the time needed for the particle to propagate. So basically, how can I quantify is that, let me label this t here with delta t instead of t. Delta t is the time interval that we want to calculate this probability. And let's say when x final minus x initial, let's call x0 x initial, is so much larger than the delta t, and we know we are just dropping the speed of light, relationship between space and time become very direct. So then that means that there is not enough time for the particle to propagate into that point. So it is causally not really convenient. So we still respect causality here. I don't know if you hear probably some of these popular videos recently, is causality violated? These are really, in the context of quantum mechanics, even causality is a matter of discussion right now. There are many definitions of causality, but however, in the scale that we are right now, we care about causality. That means that we cannot really send out the electron outside of the light cone that it can go on. So to keep this causality alive, we cannot rely on particle relativistic quantum mechanics. So let's say relativistic particle description. And relativistic particle description, that means that if I have xi and xf, and I write down the Hamiltonian like e to the power of minus I, the Hamiltonian was the square root of m squared plus p squared delta t. And this is like a form of operator here. It's a little bit actually not convenient to write down an operator in the form of a square root, but we have to consider the square root is a kind of operator that is smooth, so it can be Taylor expand on the power of m. So the square root of m squared plus p squared is as an operator, let's say as an operator, is m squared is basically not an operator. There is a basically unitary operator behind m. M is just it's a kind of coefficient here. And then we have, let's put it I here. So that could be expanded based on some p epsilon as a power. So there is no huge conflict here how to somehow diagonalize this behavior here, the behavior of this operator. But however, when we calculate this number, which is the propagation amplitude, when the delta x is so much larger than delta t, this is not somehow equal to 0. It's a non-zero number. So even when we try to put relativistic correction on a particle description and calculate the propagation of the particle outside of the light cone, we get a non-zero particle. And you can find out the actually the correct derivation of this equation, that exactly how much is this number in the textbooks such as Peskin. So we have all these reasons to go to quantum field theory, and now we want to define what exactly a field theory is and what's the difference between a classical field theory and a quantum field theory. Okay, the word QFT means field description plus quantum effect. Quantum effect. And we previously talked about the field. We understand the meaning of field from classical field. Classical field. A classical field is what? Is the mapping between a space-time that we call them a static coordinate. That means that they don't change, they are not dynamical, they are just the way that we label the space and time into some variable that let us start with the most simple kind of field, for example, a scalar field. A scalar field is basically one number. It can be a real number or it can be a complex number, but however, it's a value. So we understand the field idea of the field with the value. And this value is somehow averaged value. So we talk about coarse graining and how fields are effectively explained, but somehow the classical fields such as electromagnetism, hydrodynamic, these are like a kind of classical field that we understand them. But when we are talking about quantum effect or any quantum procedure, let's say, that means that we have to deal with the objects like that. So there are two state objects, a state prime and a state. And then you have some evolution, some operator here. I just label it with O. And these are like quantum mechanical amplitude. And when we're talking about adding some quantum procedure, that means that we define everything in a form of a state and then in a form of operator. So a state is defined by, let's say we can label a state as psi. So psi is a very convenient name. Let me write it with the white color. Psi, let's say, is a state, and a state belongs to a Hilbert space, and a Hilbert space is a kind of a space that allows us to have supersymmetry, a superposition. I said supersymmetry, superposition, and also infinite dimensional space. So the difference between Hilbert space and ordinary space that we are dealing around is that a Hilbert space is a larger construct and it can have infinite number of dimensions. But the interesting thing is that the state can be expressed in terms of operators. So the dimension of the Hilbert space is determined with how many independent bases we can find for a Hilbert space, and somehow a Hilbert space can be spanned by operators that can be expanded into certain observables. So the definition of a state is some address of the system. So a state is some vector in a Hilbert space that can tell us where is the system or where is the physical system is exactly located. So let's say a state is labeling location of system, and by location I don't mean let's say physical location. That could be one operator. So that would be interesting. We're going to express it right now. So the location of system in some space. So the state can be expressed in terms of, let's say, X operator or P operator for just a single particle. And we are not talking about the field here. And then we can express them a space based on the X basis or P basis. And those are just providing us the quantum description of the system. But the important thing is that the observables are operators, and the observables define how to express an state. So we have the Hilbert space that define the state of a state, and then we have another Hilbert space of the operators act on physical state or a state of the system. So we can define somehow two Hilbert space, the kind of space that the state can be addressed in, and then we can also express how many operators we can define with certain symmetries to evolve those space in that particular Hilbert space. And so the definition of quantum physics is basically the states, and then the state evolve. So the time evolution is usually encoded in Hamiltonian, and then we have a final state. And this is like quantum procedure, calculating quantum mechanical average value. And there are certainly three pictures of quantum mechanic. So there is one picture stating that the state can be time dependent. So a state is time dependent. There is another, this is called the Schrödinger picture. And then we have another perspective here, Heisenberg picture, saying the states are not time dependent, the operators are time dependent. So this is called Heisenberg picture. And how they are connected to each other is that both of them somehow is stating that the evolution of expectation values are the same in two pictures. And then we have the interaction pictures. Interaction picture, which is a mix of Heisenberg picture and a Schrödinger picture. It is basically saying that the states are evolved with free Hamiltonian And the operators are evolved with perturbative Hamiltonian. So basically stating that if we have a state and then there is a free time evolution, that means the evolution is from h0 t, and this t is the providing time, and then we have the evolution of final state, again in a form of free Hamiltonian, and then we have in between the perturbative interaction that can be seen as an exponential of IH perturbative, let's say H prime delta t, which is the interaction time, and then we have two different operators. So the operators, let's say the operator in between, the interaction operator, is evolved like this: e to the minus I perturbative Hamiltonian delta t, and e to the plus I perturbative Hamiltonian delta t. So this is the interaction picture, saying the green part here is the perturbative and like Heisenberg-like picture, and these two yellow expressions are the Schrödinger part of the evolution. But the point is, the expectation value in the final state does not depend on the picture that we are looking at. Even if we have Heisenberg picture or Schrödinger picture, interaction picture. So interaction picture somehow is a kind of approximation of the mixing of Schrödinger picture and Heisenberg picture, but Heisenberg picture and Schrödinger picture are the same. So now we talk about Hilbert space and a state and operators. Now we can have a definition of the classical field. So the definition of the quantum field is a mapping from a static coordinate of x and t into a phi, which is an operator. So it is basically phi of x and t. And simply is just saying that if we are having a kind of volume here, so this is what we are doing in quantum field theory. And imagine that we are labeling this volume with a static coordinate. So that means that we don't really have a problem of defining space and time. And you're going to see in quantum gravity, and when we're trying to write a quantum field theory for gravity, that would be a little challenging because the space and time are then dynamical. But the point in quantum field theory is that the space-time is flat and static. So that means that we can have a kind of labeling system and then use to measure any points in this coordinate system. So imagine now I define at each point of this site some dynamical variable that I call it phi operator. This is similar to x or p operator in the particle quantum mechanics, and I just label it with x and t that it is inside of it. And the point is that this coordinate here, this labeling, can be transformed into another picture. So imagine that I have the same box here, and then I choose to define new kind of coordinate here that imagine they are not like other coordinate. Imagine they are a little bit different. They're not here in graphic representation or perpendicular to the box. And imagine I want to label my box like this, and the other probably direction of it is this. And imagine this is called x prime and t prime, and even the map between x and t to x prime and t prime would be a map between phi as a function of xt into some phi prime of x and t prime. And there is a mapping, so we have to understand what are these mappings we need to understand. And this is coming from Lorentz transformation, symmetries, that we're gonna talk about it when we start to work out on the Klein-Gordon field. Basically, the simplest field that we can deal with is the scalar field, which is not complex, so it is a real valued, and then a real valued field. We're gonna see it's the most simplest entity that we can define, and then we can define the Lorentz transformation and the symmetries and see how we can calculate very interesting variables out of them. So a quantum field theory is just saying that at each point of a space-time, let's see, I'm putting a device here, and device of measurement is just measuring the random value of the field. And for example, I say phi 1, phi 2, phi 3, phi 4. And the same principles of quantum mechanics is just basically saying that all of them are the eigenvalues, They're eigenvalues of phi operator. Okay. Now, that's the difference between quantum field and classical field. And let's talk about Feynman path integral, because that is also very important topic here. Feynman path integral formulation. So Feynman path integral is a classical interpretation of quantum mechanics. So Feynman was basically arguing that if we want to calculate a quantum mechanical amplitude, let's say initial and evolution and final, he told us the classical interpretation of it is that the particle from the initial point to the final point. In a classical physics, for example, imagine that we only have one trajectory that could be seen as the minimum action trajectory. So the minimum action trajectory. And Feynman said, no, the particle can go all of these possible routes from initial point to the final point. Imagine that I have all of these crazy paths. And then the possibility that the particle is in each of these trajectories is proportional to the exponential of I times the action, or minus I times action. But the point is, this probability is something not normalizable, that we cannot really normalize it, because all of the actions, even the minimum and the maximum actions, are multiplied in an imaginary number, and that basically allowing all of the trajectory to contribute into the final trajectory. So Feynman path integral is saying that the quantum description of one particle propagating from one point to another point in a certain physical dynamic that it is encoded in Hamiltonian, this can be seen as the summation over all possible trajectory. And this is the Feynman path integral. And you might ask the question is very valid, that how can we exactly calculate these integrals? Because if we have infinite trajectories, if we are able to calculate infinite trajectory, how can we practically calculate this integral? So there are ways to deal with that. So one of them is rotation in the real time to imaginary time, and basically going from Lorentzian spacetime to Euclidean spacetime in lattice QCD. This is a common method. And then we can do some calculation, and we can somehow systematically evaluate a path integral. So the way that our computer calculates the quantum mechanical amplitude is to do the path integral. That means that, for example, in the case of one particle, if we just say the final and initial state are fixed and the dynamic is in between is defined, then what's the probability that particle goes into one of those paths? And we know there is two formulation of classical physics. There is a Lagrange formulation, and we have the Hamilton formulation. And they are both the same. That means that both of them just predict the evolution of the system. The Lagrange formulation, we have two fixed boundary condition. And then one unique trajectory. And in the Hamiltonian formulation, we have the initial state and we have the initial momentum. And then we have the Hamiltonian, and we basically can calculate the behavior of the system in the phase space. So where does it go? Even if we have a space of x and p, if we just have the initial state, we can exactly follow what's the trajectory of the particle. And we know a Lagrange formulation is more friendly to quantum mechanics. And Hamilton formulation is also friendly, but there is a little difference between quantum mechanics and classical physics. In the Hamilton formulation, the problem is that for exactly predicting the trajectory of the particle, you need both of the xi and pi, which you cannot do it in quantum mechanics. In quantum mechanics, you are not able to know what's the initial location and initial momentum, and that's why we have this Hamiltonian evolution of the system in quantum mechanics. But the situation of the system is not labeled with the initial location and initial momentum, but the Lagrange formulation is more friendly because Lagrange formulation, we only know the initial location and the final location. We don't know anything about the momentum. And that's basically quantum mechanics. In quantum mechanics, you cannot know two variables that are like conjugate of each other. Momentum, space, time and energy. We're going to talk about them. We're going to see them more in mathematics. They're emerging out, the similarities and the difference between them. But in the Lagrange formulation, you basically have initial state and final state. And you say, if there is only one trajectory, that's classical physics. And if I have all the trajectory in the same weight, in the same probability, that's quantum mechanics and that path integral formulation. So path integral formulation can be extended into field instead of one particle. So in a field, let's say, imagine that in the particle I have something like this. I had x and I had t. And again, this t was the static coordinate. And then x was the dynamical. When we are talking about field, we are just bringing x into the same level of time. So here I have xt, let's say, imagine, this is just one line, but imagine this line is multidimensional, and then I have this phi. So this phi is my field, and it's very similar to x. It's like a kind of location, right? And then I have the phi initial, and then I have phi final, and then there is x, and then all of these are possible evolution of the whole field configuration in a space-time that contributes into the existence of a quantum field. So a quantum field evolved. If we think of a quantum field system, imagine if I have a kind of system that it is in the initial state, and if I let it evolve, it evolves in many ways. Imagine this is the initial, and then this is the final, this is another way, this is another way. Imagine all of these graphical representation are different scenarios. Do you remember in Rick and Morty, they have all these different parallel universes that everything is happening with crazy possibilities. Imagine all crazy possibilities can happen with the same amplitude. So that's how quantum fluctuations are not negligible. One difference between quantum fluctuation and thermal fluctuation is that we can avoid thermal fluctuation if we increase our precision or bring down the temperature. But quantum jitteriness or quantum fluctuations are like this, that all the trajectories that are even craziest having the same probability is just creating one big quantum jitteriness. And out of this, we need to find meaningful expression to calculate the relative amplitude. So any crazy thing can happen. Any crazy configuration of the field, any crazy evolution of the field can happen, but the relative ratio of them is something under our control. So we cannot, for example, exactly calculate how does a field evolve. We say on the average, how does the field evolve, and then we can add some correction into that. So we have this Lagrange formulation and a path integral formulation. Let me write down the mathematics of path integral formulation. So a state can be expressed in the form of, let's say, space-time, energy momentum, and even maybe other kinds of, but in the context of quantum field, we just have this static coordinate, space-time and energy momentum. So I can say this is EP and this is TX, and then all of them have this kind of Lorentzian signature. For example, the energy momentum for the on-shell particle, E squared minus P squared should be M squared. So there is also a relationship between those coordinates. They cannot be all the possible configuration, but they're different in terms of nature. So energy and time, and then X and T. So we usually want to express this state in the form of energy momentum. And there is a good reason for that, because when we say we provide the system in one particle state, that's more accurate to say I provided a state in exactly what location. So usually we go to energy momentum state, and we usually always define something that we call it vacuum state. Vacuum state means the state that there is nothing basically external. The only thing that exists are the quantum field on this background, and then we want to calculate many things in expectation values for the ground state. Well, let's say this is called the ground state. And probably for those who have quantum mechanics course, quantum mechanics previous in the previous experience, they realize that ground state is something that it is defined for a simple harmonic oscillator. So a ground state is something very interesting about ground state, is that we think ground state has zero energy, but it doesn't have zero energy because it is violating uncertainty principle. So the ground state energy is not zero, and it is somehow related to uncertainty principle. So ground state can really express uncertainty in a very good way, that there is no way that we understand something is in the zero level, because there is always some jitteriness, some fluctuations for the field. And usually the operators are defined in a space-time. So that's how we can separate the physical state with the label of energy momentum and the operators in the form of a space-time to kind of create a connection between space-time and energy momentum. So in quantum field theory, we want to calculate something like this: 0, the expectation value, and then evolution of the system, which we said is provided with the perturbative Hamiltonian, delta t, or even real Hamiltonian, and then 0 as the vacuum state. And this can be expressed in the way that I have a kind of field from this expression here. This expression can be calculated with path integral, which is basically saying that if you look at the classical system here and you want to calculate, and imagine I have an operator here. Now, what's the path integral? Path integral is saying that if you have a state here, let's say you define a state here, maybe in the energy momentum, even in the vacuum. Let's say I can call it state P and a state P, and then you have some operator that you want to calculate the expectation value, and then on the two sides you have the evolution of the system. And how do you calculate that? Basically, is that you classically think that there are classical integrals and the Lagrange formulation, that you calculate the O as a value as a kind of x and t value, O of phi, let's say. Phi is the dynamical variable, so O is a function of phi. And then the probability weight for it is minus action of the phi. And then we have this phrase d of phi. D of phi means all possible trajectories of the particle. And then it should be normalized to the weight without the dynamical variable that we want to measure the expectation value of it. This is very similar to partition function. Partition function in statistical mechanics is very similar into this, that you need to sum up all possible ways that the system can evolve. So it's like an ensemble, then calculate the expectation value based on how many trajectories you have. And these integrals are really not, we are not really able to, we are able to calculate them with some tricks. So, but if you think about them computationally, they cannot evaluate infinite number of the trajectories that that we can have. So numerically, we cannot really approach this problem because there are infinite trajectories that we can make. But with some tricks, we can even bring it into the control of numerical calculation. But with some mathematical formulation, we can use path integral to, for example, calculate the propagation amplitude. So we are going to talk about path integral so much further than that. So we are going to basically talk about Klein-Gordon field. And then we're going to talk about QED, quantization of fermions and bosons. And then we are going to go into path integral formulation to see how we can drive those propagators with the path integral formulation. But path integral formulation is beautiful because it is the human interpretation of quantum mechanics. And it is just basically saying that if you have initial and final state effect, everything can happen. Everything can happen in between. And somehow we need to understand on the vacuum states what's happening. So we are interested more in the vacuum state. So almost the time is up. I just want to finish with one point about function and the functional. So Lagrangian of the field is expressed as the summation of the kinetic term, which is written as Lorentzian signature of the derivative. So that basically means mu 0 phi, mu 0 phi, right? Minus mu 1 phi, mu 1 phi, and so on to the other dimensions. So this is representing the kinetic term of it. And then you have, let's say, phi squared term, which is the interaction term, let's say self-interaction term. And this is a Lagrangian that is the function of phi, but this is not a function of a space and time in a form of explicit way. And you might ask, what does it mean? The field is a function of a space-time, so xt is mapped into phi, and then phi mapped into the Lagrangian. But the relationship between Lagrangian and x and t is not explicit. That means that if I take a partial derivative of Lagrangian in respect to time or a space point, I should get 0 terms because I don't have any explicit dependence on the space and time. And that makes sense because our physics should be independent of the way that we label the coordinates. So we label a space-time with different methods, and none of them is really better than the other one. So the Lagrangian that has the information about the physics should not explicitly depend on a space and time, because that violates the principles that we don't want to be violated. For example, if the Hamiltonian have explicit dependence on time, then that means the energy conservation is going to be violated. So we express like O operator in here on the path integral. I express O as a function of phi. The reason that I didn't write it as a function of a space-time is that a space-time is not the context of path integral. Path integral is not worried about a space-time, it's worried about the dynamical variable that define on the space and time. And we have something that it is called a functional. So functional means that you feed a function into a machine, and the machine gives you a value, right? And that's a functional. And a very good example of it is the action. So action is a function of phi, but we want to integrate it over any trajectory that the phi has, so d of phi. So we are feeding a function into a functional, so we integrate that function and then we end up in a value. So the value, the expectation value we get from Feynman diagram is coming from a functional. So that means that different forms of phi function can be fed into this machine and then we can get a value out of that. So that was the very introduction discussion about the philosophy and the motivation of why do we go into the quantum field theory. So let me express the summary very quickly here. So at the very early beginning of the session, we talk about what's the difference between classical physics, quantum physics. We talk about de Broglie wavelength and where the de Broglie wavelength is comparable to the size of system. We talk about elastic and inelastic nature of quantum. So when we have elastic quantum, we can use particle quantum mechanics, and then we have inelastic quantum mechanics. We need to go to the field because we can create and annihilate particles, and this is the energy scale. And then we talk about relativity, how relativity can be important. We said that there is nothing such as the correct particle relativistic amplitude, and we can actually calculate this integral in one session precisely. But to see that it is outside of when the particle is propagating outside of the light cone, we just see that this is not going to work. And then we talk about QFT and say what's the QFT. So the overall understanding of the QFT is this field that we understand it from the classical field, and it was like a mean field approximation. It's an average value, or it is like a quantum expectation value. And then we talk about Hilbert space as a quantum entity, and then how a state and operators in different pictures, a Schrödinger picture and Heisenberg picture, can be evolved. And then we talk about the interaction picture, that how can we possibly separate free part of the Hamiltonian from the interactive part of Hamiltonian, which is perturbative. And then we talk about quantum field as an entity. So field is an operator defined on the Hilbert space of physical state, and there are transformation between these space-time coordination. And then we have to somehow construct a space-time independent or coordinate independent physics out of that. And then we talk about Feynman path integral and how classical interpretation of quantum mechanics can be used to calculate quantum mechanical amplitude. That means that all the trajectories and all quantum jittery behavior are possible. All the paths are possible with the same somehow probability amplitude, because the action is proportional to a complex number, and we can talk about it later. And then we talk about two formulation of classical physics, Lagrange formulation and Hamilton formulation. And we say in quantum mechanics we cannot measure the initial state of the system very accurate, so that's why we only have access to final state and initial state in the same basis. Let's say both of them should be expressed in terms of x, not p. And then we talk about path integral, and then how path integrals are somehow connected to functionals. Functionals of actions are just taking a function, and that function is the dynamical variable that we call it a field. So I hope in the next session I'm going to start with Klein-Gordon field. So first of all, we're going to see what's the classical behavior of the Klein-Gordon field. What's the classical meaning of it? Because there is a lot of interesting information in the classical way that we are looking at the field, such as Noether theorem. Noether theorem is not something dependent on quantum mechanics. So Noether theorem is a mathematical theory that just talking about symmetries in fields and then some currents that are carrying the conserved quantum numbers. And then we're going to quantize it and see what's the meaning of quantization of the field and how quantization can encode Feynman diagrams. So I think that was Steven Weinberg said quantum field means Feynman diagrams, and then Feynman diagrams are very interesting, and we're going to see how simple Feynman diagrams can be taken out from Klein-Gordon theory. So thank you so much for watching this, and I hope you have a good day.